Hi everyone! In today's lesson, we're going to go over how our solar system came to be and therefore how our planet Earth was initially formed. So let's start the exploration, shall we? So first and foremost, I want you to consider this picture. So if you take a close-up look here, let me make it bigger, you can see that there's tons and tons of little specks. If you look closer, you'll see that some of these specks are actually galaxies, some of them are stars, but all of this is something that we can see in a little corner of space. This picture was taken by the Hubble Space Telescope, and again, just in this little picture here, you can see millions and millions of galaxies and therefore billions and billions of stars. Again, each one of these is actually a galaxy. And if we take an even closer look here. So there's the picture blown up. This picture comes from this corner of the sky. So here is our moon for reference. So this little corner here from right to the left side of our moon, it was zoomed in by the Hubble Space Telescope, and then we get this picture. So this entirety of all of these galaxies can be seen only in this teeny tiny corner of the night sky. So what that tells us is that our universe is composed of billions of stars and billions of galaxies. And what we can see is just a mere fraction of all of that. So how did this all come to be? The best estimates that we have is that around 15 billion years ago, there was an event. And that event we're going to call the Big Bang. And then since that event, the universe has been expanding outwards, getting bigger and bigger and bigger. And something cool that I mentioned in class is if you look up at the night sky and you're looking up at the stars that you can see, what you're actually doing is looking into the past. So the light that we get to see on Earth today was actually generated in stars millions and millions of years ago. We're only just starting to receive that light now, which is why we can see it. So that's why here it says the furthest supernova. So if we're looking from from Earth and looking back and we see a supernova, that supernova did not happen yesterday, did not happen the moment that we see it. That supernova happened millions and sometimes even billions of years into the past, and we're just starting to see it. So again, the universe began to expand. We had this Big Bang event, and ever since then, the universe has been expanding outward. So if you want to be even more poetic, there's this poem by Robert Frost that says, the world could end in fire, the world could end in ice. And if we're going to subscribe to this and this constant expansion outwards, right? So eventually, since we're all moving away from each other, we're all going to just drift out into the coldness of space. So ice wins. But don't worry, that fate of just drifting through the emptiness of space is still billions and billions of years away. So we won't be there to see it. So this answer to the question, where did we come from, that I very quickly summarized. And again, if you're more interested in learning about the formation of the universe and its history, please take in one of our astronomy classes. They're very, very good and they explore this in detail. But all of this is to say that where we come from, how things originated, has been a question that we've been trying to answer as humans for thousands and thousands of years. And initially, back during the Middle Ages and before, we had these models that helped explain what we saw in the sky. And the first model of our solar system, essentially, was very much of what we call a geocentric model, where the Earth is in the center of that system. And then there's different spheres around the Earth that have different parts of the universe that we could see in the night sky. So that first initial sphere is where the Earth is, and then the moon is in the closest sphere to the Earth. Then we have Venus, then we have the sun, then we have Mars, and then beyond that, we have the rest of the stars that we could see in the sky. And part of the reason for this idea is that we could see certain planets move across the sky in a different way throughout the year than other stars did. So humans observing this from Earth thought that those were in a different, basically, sphere. If you were to see this as those little Russian nesting dolls, the Earth is the smallest doll in the center, and then each slightly bigger doll would be one of these spheres that would kind of go outward. So these ideas we now know to be flawed, and even though it could explain some of the things that we saw in the night sky, it didn't explain everything. And it wasn't until way later that we have what we now call the heliocentric model. So the heliocentric model just says that instead of having the Earth in the center of our solar system, we're actually going to have the sun. So the geocentric model, geo from Earth, right, from Gaia, the Earth is in the center. The heliocentric model, so helio comes from the Greek for the word sun. The sun is in the center. So in the heliocentric model, we have that all of the planets are going to be rotating around the sun, and the Earth is just one of many planets that is currently doing this. Whereas in the geocentric model, we have that the Earth is the center of the universe and everything else is spinning around it. And here I want to point out several individuals that were responsible for our understanding of this heliocentric model. We have Nicholas Copernicus, who was a Polish astronomer and the first person to actually suggest that it was the sun that should be in the center of our planetary system and not the Earth itself. We have Galileo Galilei. So he was a big proponent and supporter of Copernicus, and one of the cool things that he did, besides really annoy the Catholic Church in the 1600s, is he actually observed Jupiter and its moons. So he saw that the planet Jupiter had little moons, little objects that were actually spinning around it. So if Jupiter had moons, so Jupiter had objects that he could see were going around it, then definitely the Earth wasn't the absolute center, because Jupiter had things that were going around it, so not everything is spinning around the Earth. Then moving on, we have Johannes Kepler, and he was one of the people that was responsible for defining the orbits of the planets in the sky. And then, of course, you've heard of Isaac Newton, the apple guy, even though that is a myth that never actually happened that way. But Isaac Newton actually formulated the laws of motion and of universal gravitation, which has become the dominant theory for, the past several hundred years. So we have Newton to thank for that. Understanding that the Earth is not the center of our solar system, but instead the sun is, we come up to how did this system form in the first place. And from what we know and what we've been able to date, our solar system is about 4.6 billion years old, and it formed when you had a gravitational collapse of a molecular cloud. So you have this cloud of different elements that basically begins to spin and then kind of collapse on itself, with all of the heavier items going to the center of this molecular cloud. And then eventually, through gravity, different parts of this cloud are going to start to differentiate, and then we're going to have a proto-sun, which is going to have the most mass in this molecular cloud. And then eventually, because things start to differentiate as they start to orbit around the sun, and again, they orbit because of gravity, right? This is the biggest thing with the biggest mass, and then everything starts to kind of shape its way around it. We're going to have the accretion of different planets, be them gaseous planets, like the ones that we have in the outer solar system, or rockier planets like, Mercury, Venus, and Earth. And to bring it back, Newton's laws of motion and gravity help explain how all of this would happen. They help explain how all of these materials would start moving in this planetary disk, and how gravity would help accrete the different planets together. So it kind of all goes hand in hand. So our solar system, and again, there's many different parts of the solar system, but all in all, it's composed of the sun, of course, at its center. It has 8 planets that are going to be orbiting around that sun, but it also includes all of the moons that those planets have. It also includes comets that might be gravitationally bound to our sun and have these orbits that bring them close to the sun every so often. It also includes the different asteroid belts that we have, and all of the material that is gravitationally bound, again, to our sun. All of it composing our solar system. And it goes way beyond the orbit of Neptune as well. And here we have a little illustration of what our solar system looks like. This is not to scale. So we have our sun, we have Mercury, which is a rocky planet that is the closest to the sun. We have Venus, or our twin planet, even though, there's a lot of things about Venus that are very different from Earth. Size-wise, it's very similar. We have Earth. Earth is where we live. We also have our moon. We have the planet Mars. Mars has 2 moons, and Mars is just outside of the habitable zone of our solar system, but we have a lot of interest in Mars. Then we have an asteroid belt that divides our inner planets from our outer planets. We have Jupiter, which is the largest planet in our solar system. We have Saturn, which is well known for the rings. We have Uranus, our diamond ice planet. We have Neptune, and then that would be the end of the planets, all right? So we used to have this guy right here, Pluto, but Pluto has since been demoted from being a planet to being a dwarf planet, and mostly because of very big differences between how all of the other planets behave with respect to Pluto. For instance, all of these other planets are orbiting the sun more or less at the same level, whereas Pluto is kind of diagonal to all the other planets, which is part of the reason, or one of the reasons, why Pluto was reclassified of being a Kuiper Belt object instead of a planet. Let's take a closer look at our inner planets. And again, the ones that are part of the inner solar system are Mercury, Venus, Earth, and Mars. And these 4 planets are rocky, all right? Even though Mercury and Mars are significantly smaller than Venus and Earth, these 4 planets are similar in that they have a rocky crust. So they all formed in a very similar way by aggregation of that material that was spinning in that planetary disk. They have been partially or fully molten at different parts of their geologic history, and they were heavily bombarded by asteroids. So today, we don't see as much of this bombardment by meteorites as we did in the past because of the debris that used to be roaming the solar system has kind of fallen into place. But early on in the solar system's history, bombardment of planets by asteroids was very, very, very common. And if you need any evidence of that, just take a look at the surface of the moon. The surface of the moon is cratered in craters, which are basically the remnants of those asteroids that impacted the moon. Earth used to look just like that, but we have active plate tectonics that recycles our crust, so we don't get to see all of those meteoric impacts within our surface. So taking this a step further, we can ask the question, why did life develop on Earth the way it did and not on other planets? Mind you that we're still trying to answer this question to varying degrees. For instance, there is really good evidence that there might have been life on Mars that we are now just getting from our Mars missions. But life as we know it, and emphasis on as we know it, seems to have only developed on Earth. Earth is the only planet, as far as we know, that has all the variety of life that we do. So there's something special about the conditions for life that were met on Earth. And one of those things is the abundance of water. All right, so Earth has liquid water on its surface, and we know that the presence of water is very important for life. We've talked about this before in class. Everything on Earth is tied to water in one way or another, be it for drinking, be it for laying eggs if you're talking about amphibians and fish, etc., etc. We as humans are over 60% water in our own bodies, so water is really, really important. Another thing is the surface temperature of the planet. So our distance from the sun is very important for this, but also the fact that our atmosphere is a system that will filter the energy that we're receiving from the sun. So we have carbon dioxide in our atmosphere, we have water vapor, we have methane that'll help trap some, but not all, of the heat, and then will keep the surface of the planet warm. All right? Planetary size is also very important because the planet has to be large enough to not allow all of the gases of the atmosphere to just float away into space. So Earth is just the right size for this. Whereas if you look at Mars or you look at Mercury, they're a little too small for this. So as a result, the atmosphere in Mercury and Mars is a lot weaker than the one that we have here on Earth. And finally, we have to have a live planet. And what I mean by a live planet is a planet that is geologically active. Earth has volcanic activity. Okay, so that means that we're going to be recycling our crust. That means that gases that are absorbed in rocks get to be recycled and then erupted onto the surface. These gases can include water, include CO2. So all of these things get put back out into the atmosphere by these volcanic sources. And all of these reasons are why life on Earth is so important. And we actually look for these things when we're looking for possibilities of life on other planets. We look for water on Mars. We're looking for clues on whether some of these things have been available, if not now, then in the past. We are currently looking at some of Jupiter's moons and Saturn's moon Titan as a possibility for holding life. Well, we're looking for these conditions. Are they the right size? What's the temperature? Can they have water? Are they geologically active? All of these things are important for life as we know it to develop. Taking a closer look at surface temperature, we have the distance from the sun. So depending on the kind of star, all right, so we have cooler stars and warmer stars and whatnot. Our sun is this kind of star. It's a class 1 here. So depending on the star and how much energy they put out and how much heat they put out, there's going to be a different part of the orbit around that star that is going to be habitable to life as we know it. Earth, for instance, is right smack in the middle of the habitable zone of our sun. So it makes quote-unquote sense, or it helps explain how life developed here on Earth. It's because we are within this habitable zone. If you take a look at Venus is a little bit too close to the sun, which helps explain why, even though Venus has an atmosphere, they also have runaway greenhouse there where the temperatures and the pressures are just too great to support life as we know it on the planetary surface. And if you look at Mars is just out of the habitable zone, so just barely there. And Mars is a little bit smaller than Earth. So this helps explain why there isn't as abundant life on Mars, or we haven't found life on Mars, mind you, but why this might be. The planet is a little too small, the atmosphere is a little too weak, and it's just a little too cold for life to develop in the same way that it did on Earth, at least right now, to date. And this helps explain that kind of a scenario. We also call this like the Goldilocks phenomena. We have that, it's not too hot, like these two planets. It's not too cold, like all of these planets, but it's just right where Earth is. So again, if we're going to look at our planetary neighbors in the inner solar system, we have that Mercury, a little too hot, a little too close to the sun. Venus has the right size, right? But a little too close to the sun, a little too hot. We have our moon. Our moon is in the habitable zone, right? It's right there with Earth, but the moon's a little too small, and therefore it doesn't really have that volcanism, that live activity, and can't really hold an atmosphere because of the size of the moon, so too small. And then we have Mars, which is an interesting case. It seems that Mars could have held life in the distant past when it was still a warmer planet. Mars has some water. We can see here from this picture that the ice caps of Mars have some ice water. And they've also found places where there is possibly frozen water beneath the surface, and we're studying that right now. But Mars is a little bit too small and a little bit too far away from the sun. So it was not possible, if it had life, it no longer has the conditions that are necessary for life as we know it to develop. And then finally, we have Earth, and Earth is just right. Earth has the right distance from the sun. Earth is large enough to be able to hold its atmosphere. Earth has active tectonic plates, so we have that recycling of the crust. We have that putting of gases out on the surface. Earth isn't too hot or too cold. It is absolutely in the right location for us to have life as we know it develop on the planet. And on that note, please keep in mind that Earth is our one home. It's our perfect planet. And I want you all to look at this trailer with the wonderful David Attenborough, mind you, of the BBC show A Perfect Planet. That kind of helps emphasize some of these things that Earth has that make it such a unique world.
You are so beautiful.
They say perfection doesn't exist. But that's not quite true.
Can't you see?
There is one planet where every element has fallen into place perfectly. Planet Earth.
Can't you see?
From volcanoes to weather systems, ocean currents to the heat of the sun, these forces allowed life on Earth to flourish. Join me to discover how these diverse forces work together to keep our planet in perfect balance.
To me.
So this has been an introduction to the formation of our solar system and what makes this little planet that we live in so absolutely perfect for us. We are going to spend the rest of the semester exploring Earth sciences, exploring the planet, exploring the different parts that make it so, that make it just right for all of us. But for the remainder of this class period, we're going to take a look back out from the Earth and look at our closest neighbors, the other planets in our solar system. So please continue this activity now online and participate in the discussion where you will get to explore different planets of the solar system and discuss some of them with your classmates. I hope you enjoy this lesson. Have fun!